Welcome to this second video on local intelligence in wind turbines. Today, we'll focus on the wind turbine control and status agent, a fundamental component in modern wind farm operations. This system acts as the autopilot for each turbine, ensuring optimal performance. Its main function is to evaluate, compare, and make autonomous decisions in real time. This enables efficient and safe operation, constantly adapting to changing environmental conditions. The primary mission of this agent is to maximize energy production. Simultaneously, it seeks to minimize wear and tear on critical wind turbine components. It is also crucial for anticipating potential failures before they become major problems. Finally, it accurately executes the orders received from the orchestrator agent, integrating into a smart grid. The control and state agent is not a monolithic entity, but rather a set of specialized subagents. Each has specific responsibilities, working in a coordinated manner to achieve overall objectives. This modular architecture ensures robustness and efficiency. This subagent is responsible for fine-tuning critical turbine parameters. Its goal is to ensure optimal operation at all times, balancing production and durability. It works with several interconnected agents. This agent adjusts the blade angle in real time. Its coordination with rotor speed is vital to capturing the maximum available energy from the wind. It uses minute-by-minute wind predictions to anticipate gusts. The system dynamically adapts the pitch angle between -5 and 90 degrees. This maximizes the power coefficient in different wind regimes. Synchronization with rotor speed is achieved through PID control enhanced by machine learning. This optimizer ensures that the turbine operates at its maximum efficiency point. At the same time, it protects the structure from excessive loads. It is a key component for energy efficiency. The yaw optimizer aligns the wind turbine nacelle with the wind direction. This is very important for optimizing wind harvesting. A multi-sensor analysis detects misalignments and corrects them in real time with an accuracy of up to 0.5 degrees. This agent can even sacrifice individual turbine output. It does this to benefit the wind farm as a whole, for example, by reducing the wake effect. It follows the orders of the orchestrator agent to optimize overall output. A collective optimization algorithm takes into account the wake effect between wind turbines. This can reduce losses by up to 20%. Predictive control based on a digital twin anticipates movements and reduces component wear. This subagent constantly analyzes stress on structural components. It monitors the blades, hub, and tower. It adjusts control to reduce wear and extend the turbine's lifespan. Triaxial sensors and accelerometers are used to monitor stresses and strains in real time. A cumulative fatigue model, based on the rainflow algorithm, accounts for load cycles. This allows estimating the remaining life of components. It calculates specific stresses on critical components with automatic intervention thresholds. If chronic overloads are detected, it alerts the maintenance agent. This enables preventive intervention before serious failures occur. This subagent is the turbine's doctor, detecting subtle changes that anticipate costly failures. Its role is vital for predictive maintenance and reducing unplanned downtime. It continuously monitors the health of all critical components. It detects anomalous patterns that could indicate impending failures. This allows action to be taken before breakdowns become serious and costly. Its early detection capability is a cornerstone of operational reliability. This agent collects and processes real-time data from multiple sensors distributed throughout the turbine. This includes temperature data from the generator, gearbox, and bearings. It also monitors vibrations in critical components. It gathers information on oil pressures and levels. It also analyzes electrical patterns and generated power. It integrates data from all subsystems, including the generator, gearbox, converter, and brakes. The tower is also monitored for any structural anomalies. This comprehensive data collection is the basis for accurate diagnosis. It provides a complete view of the wind turbine's operating status. This agent uses artificial intelligence to identify deviations from normal behavior. It applies advanced machine learning algorithms to detect anomalous patterns. It identifies subtle deviations that precede serious failures. It informs the maintenance agent with an assessment of severity and urgency. It uses convolutional neural networks and Bayesian models. It compares real-time data with millions of historical samples. It can detect up to 18 different types of anomalies. It even identifies those with weak or intermittent signals. This predictive capability is critical for proactive maintenance. The control agent is not a passive system. It makes decisions every second. Its autonomy allows it to execute strategies even if the connection to the orchestrator agent is temporarily lost. This immediate response is crucial for safety and efficiency. For example, in the event of a sudden gust of wind, it detects the acceleration in milliseconds. It quickly adjusts the pitch angle to prevent structural overloads. It maintains optimal production without compromising turbine safety. If it detects an anomalous vibration noise in the gearbox, it identifies the specific frequency pattern. It activates a conservative control to preserve the component. It immediately informs the maintenance agent for preventive intervention. In coordination with other turbines, it may receive an order from the orchestrator agent. For example, a slight reorientation to reduce the wake effect on adjacent turbines. It executes this adjustment in a controlled and safe manner, optimizing the overall performance of the farm. Autonomous decision-making reduces response times from seconds to milliseconds. This optimizes operations even in adverse conditions or with loss of connectivity. Distributed local intelligence allows for responding to events without waiting for centralized commands. The wind turbine control and status agent does not operate in isolation. It maintains constant two-way communication with other specialized agents. This forms a distributed intelligent ecosystem that optimizes the overall performance of the wind farm. It interacts with the orchestrator agent to execute global commands and report their status. The orchestrator coordinates strategic decisions affecting multiple turbines, ensuring harmonized operation of the farm. It communicates with the environment agent to obtain wind and weather forecasts. This includes information on ice or storms that could affect operation and safety. Anticipation is key to planning. It interacts with the maintenance agent to coordinate interventions. It receives alerts about detected anomalies and schedules preventive shutdowns. This optimizes the management of maintenance resources. It also communicates with the data and communications agent. This agent manages the flow of critical information, balancing local and cloud processing. It prioritizes data based on urgency and available bandwidth. Finally, it interacts with the continuous learning agent. It provides real-world operational data to feed back and improve the models. This allows the control and prediction algorithms to constantly evolve. Implementing the control and state agent with local intelligence produces significant improvements. The results are measurable and have a direct impact on the profitability and sustainability of wind farms. These benefits are observed in several key indicators. An average 5% increase in optimized local production has been achieved. This is due to the continuous optimization of pitch, yaw, and operating conditions. Each turbine contributes more efficiently to total generation. A 35% reduction in major mechanical failures has been observed. Early detection and predictive maintenance are crucial to this achievement. Breakdowns requiring costly repairs are avoided. The estimated lifespan of components, such as gearboxes and blades, has increased by 20%. This is attributed to advanced load and structural fatigue management. Asset durability is significantly extended. In addition, unplanned downtime is reduced. Operation is safer in the face of unforeseen events. Dynamic optimization adapts to real-world environmental conditions, improving system resilience. The ability to operate safely during unforeseen events is an invaluable benefit. Local intelligence enables rapid and autonomous response. This minimizes risks and ensures operational continuity. In short, the wind turbine health and control agent is an intelligent, responsive, autonomous, and anticipatory system. It transforms each turbine into a highly efficient and resilient production unit. Its modular architecture and real-time decision-making capabilities are cornerstones of modern wind power operations. This autonomous agent technology represents a quantum leap in wind farm management. It enables unprecedented optimization of asset performance and lifespan. Distributed intelligence is the future of wind energy. In our next video, we'll delve into how this system uses weather data and predictions. We'll discover how the environment agent reads wind, risk, and production. we'll see how it anticipates future conditions for even smarter operations.